Let's go back to the this is the differential equation, and for piecewise constant, let's say Vs, if Vs goes from 0 to let's say 5 volts, Vc will assuming it's initially 0, it will slowly build up to 5 volts. This is the solution we have already got. Okay. And how did we say that the step will start from 0? Because it was 0 before, and then there is no change at t equal to 0, it will remain at 0. Okay, the capacitor voltage will remain at 0 and it will start building up. Okay. So now let me modify the circuit a little. I have another capacitor. What will be the order of this circuit? Okay, please again derive the differential equation, we will see. This current through R, current through C1, the total equals the current through the capacitor C. The current through the capacitor C, what is that? C dVc dt, and that equals current through R, which is Vs minus Vc divided by R, plus the current through this capacitor C1, which is C1. Okay. So if I group the variables to the left hand side and also you put it in the normal form, I will get Rc plus C1. So that takes care of this term and that term, plus Vc. So there goes that one. Then equals Vs plus Rc1 dVs by dt. Okay. But what is it that you notice here? What is the order of the differential equation? 1. It is still first order. Okay. So please think about this. Now this is a circuit with two capacitors, but when we derived the differential equation, we saw that it was of first order. Okay. What was the differential equation in terms of this capacitor voltage Vc? R C plus C1 time derivative of Vc plus Vs plus Rc1. Okay. So the highest derivative of the variable you see here is 1. So this is a first order differential equation, and consequently this circuit is also a first order circuit. The order of the circuit is nothing but the order of the differential equation that governs the circuit. Okay. So why does it come out to be first order? Should I expect a first order relationship here, or okay, let me take some other circuit which you can try out writing the differential equation for. Okay, and let's say it's also driven by Vs. You can pick any variable and you can try this out later, but you will find that the equation that you get in this will be second order. Okay, because of the presence of two capacitors. So what is it that makes this first order? Now what I have highlighted here is the left hand side, okay, which is the homogeneous part if I reduce the right side to 0. Okay. Now what condition does the homogeneous differential equation correspond to for the circuit? The homogeneous differential equation also describes the circuit, but under what condition? Vs equal to 0. Okay. So the source free circuit, when you set the source to 0, the differential equation that governs the circuit is the homogeneous equation. Okay, so that's why the right hand side is 0, the input is 0. Okay, so what does it mean? And in that condition, what happens to the circuit when Vs is 0? So when Vs equals 0, I have R, C1 and C. So how many capacitors do we have? 2. Like in the previous circuit also, just because I draw C1 and C2, that doesn't mean there are really 2 capacitors, right? It's just the 2 can be absorbed into 1. Similarly here, these 2 capacitors are in parallel, isn't it? In the source free condition. So that's what makes it a first order circuit. And in fact, you can determine the time constant from this, isn't it? What is the total capacitance you have? What is the resistance across it? R. So that's exactly what you see here, right? Of course, this is the time constant only if the coefficient here is 1, but I have normalized it like that. So the point is not how many capacitors I draw in the circuit. So first you set all the sources to 0 and then you merge all of the possible parallel combinations into a single capacitor, right? For instance, in this case, you know very clearly that this is a first order circuit with an effective capacitance of C1 plus C2. So the same thing happens here also. It's slightly more complicated because with Vs present, it's not obvious that they are in parallel, but if with Vs set to 0, it is very clear that they are in parallel. Okay, so it is very much a first order circuit. Okay, you have a different circuit where R, C1 and C are in series. So that's not the case here. In fact, those two are in series. Series connection means that KCL forces the current through them to be the same. So they are in series. Okay. So now it turns out that the series case is slightly more complicated. There are some subtleties involved. Okay. But for the purpose of this course, let's say you want to find the order of a system, you set the sources to 0, then you merge all of the possible series and parallel combinations into single capacitors, then look at how many capacitors are remaining. That's the order of the circuit. And of course, in this case, we will be dealing only with the first order system. And you also find the time constants in the same way. Okay. So you reduce the entire thing into a first order network. That is, you do all the merging of parallel and series capacitors, you will get a single capacitor. Then you find what resistance appears across that capacitor. That effective capacitance times that effective resistance is the time constant. Okay. So yeah, I mean, if you have C1 and C2 in series, you take it as a single capacitor value C1 C2 divided by C1 plus C2. Okay. So this is also a first order circuit.
So that's how you determine the order of a circuit, by counting the number of effective capacitors. As long as the order is 1, the methods we describe in these lessons will apply.